Welcome to the Newton tutorial series. I'm Mike Cruz with AC-Tek, and with this tutorial I'm going to be discussing the options on the General tab of the Surface and Material Visualization window. But before I talk about that, I wanted to expand a little bit about the adaptive degradation that I mentioned in the last tutorial. I've got that same file open that we were looking at. So if we look at some particles here, if I take and pan the model, you'll notice that it looks like the particle coloring or the particle shading is changing a little bit, but that's not actually what's happening. Same thing when I zoom or orbit. So if I zoom in, I'll show you what's going on here. Now, the spheres are actually being drawn as a set of three orthogonal lines to represent the position of each sphere. And the reason that Newton is doing this is because it's detecting that there's a significant number of particles in the current view, and in order to prevent the rendering from being too slow or too choppy, it's degrading the quality because lines are a heck of a lot easier to render than spheres. So I had mentioned that if you wanted to turn this option off, you can simply go to Particles, Disable, and that's like that's just for temporarily disabling that adaptive degradation. But the actual settings for the adaptive degradation are under File, Preferences. In this Rendering tab, there's a section called Adaptive Degradation. And what this allows you to do is set the controls independently for panning, orbiting, and zooming. So when you turn it on, that forces Newton to always use adaptive degradation when you pan the model. It forces it to always render the spheres as lines. And this might be useful if you were, say, working through a VPN or through the network, so that you have a slower connection and the file's not on your local PC. You can just always use that adaptive degradation to speed it up a little bit. If you set it to auto, then Newton will automatically determine whether adaptive degradation should be applied based on the number of particles in the current view. If you turn it off, Newton simply will not use adaptive degradation for that function. So if I turn pan off and leave these ones at auto, then when I pan the model, there's no adaptive degradation. But if I orbit it, or if I zoom it, it still uses it. The render delay is after we're done panning or orbiting or zooming, how long does Newton wait before it re-renders the scene at the normal quality? And usually a value from 500 to 750 tends to work pretty well there. Alright. Let's look at this SMV window. So you'll notice these buttons here under Surface Style are very similar to the settings in the Surfaces submenu of the right-click context menu. So basically these control the style of the surfaces, again a global control, so I can make them hidden, solid, transparent, wireframe. I can hide or show the outer lines, and I can also change the transparency. There's also this simple transparency mode that's enabled by default, and I'll show you what that is. The classic transparency mode for Newton had a few issues. So if I hide the outer lines, you'll notice that my transparency looks pretty good here. You can see everything pretty well. If I turn it back to the classic mode, you'll notice that it looks like we're missing some surfaces. We're missing some faces at the back of that pulley. We're missing our belt scraper right here. If I turn simple transparency back on, now you can see those again. Now, if I take the model and rotate around to the back side here, there's my belt scraper. If I rotate back to the front, it's missing. So what's going on here is there's an issue with the normal vectors, the front and back side of the triangle and the normal vectors. And by using simple transparency mode, we completely ignore all of that. The only downside to simple transparency is that the transparency always needs to be set in the range of 80 to 100% transparent. You can't make it any closer to nearly opaque. So if we wanted to do a full transparency sweep from 0 to 100%, you can't use simple transparency. Then you can do a full sweep. But for most people, for most cases, simple transparency is much better because they don't really care about doing a full interpolation, a full sweep. They just want to be able to see those surfaces properly, so they can just leave that enabled. And obviously showing those outer lines as well just makes it a heck of a lot easier to see what you're looking at. You can see the edges of those layers much better. So you'll notice that as I've been clicking these buttons, the checkboxes down here have been changing. This grid controls the individual the view settings for each individual layer. So if I wanted to, for instance, let's make everything transparent. Let's say I wanted to make this receiving belt solid. Well, we'll go under those layers and say solid, solid. I want to turn off the outer lines as well. I want to make that feed belt solid too and turn off that outer line. I don't like that gold color though, so I'm going to double click on this color and select a different color for it. And you know what? I don't want to look at that feeder box either. And I don't care about the belt scraper. So using this grid, you can completely customize the view settings for all of the layers. And additionally, there are settings for viewing the triangle work and triangle force. So if I say look at the receiving belt and say click work, now that's colored blue because right now there is no recorded impact wear. We've got to play back the file a little bit. So if I go to say 10 seconds, alright, there's some particles there. Let's hide those particles and play back a little bit. And you'll notice we're generating a wear summary here now. Similarly, if I change it to force, well, we're looking at those perpendicular forces. Now the actual settings for the work and force, you know, your coloring settings and your scales are under these other two tabs, the work and triangle forces, and I'm going to discuss those in a separate tutorial. I just wanted to make note that you turn on the work and the force using this grid right here. And also one other thing to note is if I open up another instance of Newton, 1 second. In our general variables, you need to make sure you set save triangle force and work data to yes if you want to save this work and these forces. If that's set to no, then we don't record those forces and these checkboxes will be unavailable when you open up the playback file. Similarly, if I want to be looking at the cluster work or the cluster forces, then I need to make sure I select save particle force and work data. Set that to yes as well. Now, when we actually look at the particle coloring, there's a whole bunch of particle coloring modes here, and I'm going to discuss them. So let's go ahead and switch everything to just outer lines. Now let's switch our view, show our particles. Let's go ahead and zoom in a bit. Alright, so particle coloring modes. We have uniform color, which just colors all the particles the same color. You can set whatever color you want right there. Coloring by cluster type. If you click this colors box, it will open up this window here, cluster colors. So you can set the color of each individual cluster, or rather each cluster type. You'll notice that the flow is becoming more and more red as I set more of these to red. If I want to color by velocity, that's the default coloring scheme. You'll probably use that most often. You can set your min scale, your max scale, and the number of divisions. It's simply the number of divisions on this color scale here. If I want 2 divisions, or if I want 10 divisions, 10 is the max. So if I set that to 150, it'll only give me 10. Next we have the fixed Z, which is a really cool setting, and I'm going to show you that with a separate playback file. So let me grab this other file. So what we've got here is just a quick little setup where a test rig where you can dump materials into the top of this and you can watch them pour out the bottom. So let me go back to that front view. So if I happen to know for this file that my min and max bound for this particles, right here at the bottom it corresponds to an elevation of 0, and right at the top is almost exactly elevation of 1. So if I set my fixed Z to go from 0 to 1 with, say, 5 slices, now let's turn that on, and it instantly colors the particles according to their elevation, and it puts them into 5 distinct slices. And what's nice, let's go ahead and change that from 5 to maybe 8, or change it to 10. So you're getting that the particles are colored. The particles are colored instantly, but they retain that color as you move through the simulation. So now that I've colored them, if I say go from 2, let's go to 3, or 4, or 5, or 8, the particles maintain those colors, so you can actually see how they flow out of this test rig. You can see the particles down in these corners are not even moving hardly at all. And if I want to go backwards, it's going to maintain those same colors again. It's really cool. So what if I go to 10 seconds? Now let's go to 8 seconds. And now let's reset this coloring mode. You can reset it simply by changing from, change back to velocity and then change back to fixed Z. So now we've reset those colors again. Now, if I want to work my way backwards, I can even do that. So let's go to 7 seconds, 6 seconds, 5, 4. You'll notice that these particles that were not in the simulation when we colored everything, they come in as black. And everything else maintains that same color. So that kind of shows you, well, you can totally see how the particles exited our test rig. It's really nifty. Elevation is similar to the fixed Z. It colors the particles by their elevation, but it's an instantaneous coloring scheme. So there's a gradient, and as we move through the simulation, it recolors the particles. The fixed Z is the only one there that maintains the actual particle coloring. Alright, so back to our other file. So, if I open up my SMV window again, after elevation, we've got particle force, which colors the particles according to their instantaneous normal force. So let's change the scale to something more realistic, 0 to 15. Now you can see the particles in that rock box have a little more force. Particles at the bottom of the belt have higher force applied to them than the ones on the top, and whatnot. Belt velocity is pretty nifty as well. This one can be kind of confusing. So what this does is you want to enter it's used for viewing the velocity of the particles relative to the speed of the belt that they're traveling on. So let's say I'm looking at this receiving belt. Do I know the velocity of this receiving belt? I happen to know that it's moving this direction at 3 meters per second. So looking at my coordinate system, that's exactly -3 meters per second in the x direction. So if I want to look at the velocity of the particles relative to that belt, let's go ahead and set my belt velocity to -3. So now for belt velocity, these 3 text boxes correspond to the x, y, and z components. Not this min-max number divisions. That's not it. It's these. Because the actual scale that you see is retained from the velocity settings. So if I set this to belt velocity and I change this from 0 to 4, it's changing the scale. That's where it's getting those settings from. Let's go from -1 to 1, because I want to look at the velocity relative to the belt on a scale of -1 to 1. So when I change this to x, what I'm doing is I'm looking at the x component of the velocity of all the particles, and I'm coloring it according to the relative velocity, the velocity relative to the belt. So particles that are moving exactly at the speed of this belt are going to be colored green, because that's 0. So I'm going from -1 to 1. Particles that have a x velocity that's faster than the belt are going to be colored toward the red. So these particles over here, which technically they're moving to the right, as they fall through the chute, they're moving to the right very slowly. So they technically have a higher x velocity than the particles on the belt, and that's because the coordinate system is backwards, because our belt is moving in the negative x direction. So it would be a little bit more clear if our belt was moving in the positive x direction. But technically, the x component of the velocity of these particles is greater magnitude, not greater magnitude, but it's greater in the absolute scale relative to these. These are moving at -3, this is moving at -1 in the x direction. If I wanted to look at the velocity relative to this feed belt, let's go ahead and do that. So the feed belt, I believe, is also moving at 3 meters per second. So if I change back to velocity, oh yeah, let's change that back to some. I'll talk about that in a second. So my velocity here, 0 to 5, 2, let's go 2 to 4. Yep, perfectly green, exactly 3 meters per second. So the feed belt is feeding at 3 meters per second in the y direction. So let's go back to belt velocity. Our velocity is 0, 3, 0. Now our relative velocity, again, we'll set that from -1 to 1. And we change this to y, because now we're looking at the y component. And we see that the particles on the feed belt are colored red. Why are they colored red? I thought our velocity was 0, 3, 0. Was it not? Oh, because I don't have this selected. There we go. I was still coloring according to velocity. Alright, so now once I color back to the belt, we can see, yep, all these particles are moving the exact same speed as the belt. The particles that are being dumped on here have a slower velocity. You know, they haven't been accelerated yet. And similarly, the particles as they're launched off, they have a slightly higher y velocity component. And that's just because these ones on top are falling through the air. Then if I wanted to say, let's say I wanted to look at the x component of the velocity. Now what this does is, again, we're looking at the particles on this feed belt, but we're looking at the x component of the velocity relative to the belt. So the belt has 0 x velocity, but as this material falls into the drop box, the material falling this way has a negative x velocity. Remember, our coordinates are backwards. So because it has a negative velocity, it's colored blue. The particles on the right side here are colored red because relative to the belt, they have a positive x velocity. So this belt velocity is just really nice for being able to view the speed of the particles on the belt, just looking at how it's moving relative to the belt. Now this sum, XYZ sum, is used for when we're looking at our belt velocity. We can look at the velocity relative to the x, relative to the y, relative to the z. But these buttons, these XYZ sum, also applies to coloring our particles by velocity. So if I go back and let's just change this back to 0 to 5. We're just looking at our material velocity again. If I have it colored by sum, we're looking at the x, y, and z, the net velocity of the material, the total absolute velocity. But if I look at x, I'm only looking at the x component of the velocity of the particles. So you can see that all this material moving on the belt has 0 x velocity. And there's some x velocity there. If I look at y, now obviously all the material on the receiving belt has basically no y velocity, and the feed belt has a y velocity. So this is used for just changing your x, y, z component of the velocity when you're looking at this velocity or the belt velocity. So don't forget, when you're done looking at belt velocity and you go back to velocity, you're going to want to change that back to sum, or you'll look at this and say, you know, hey, what's going on? My coloring seems goofy. Oh, I forgot to switch that back to the net velocity. Next, we have the transparent. So transparency is really cool. It allows you to color just 1 or 2 specific clusters and then allow the rest of the clusters to be transparent. So if I say 1 to 1, this means I'm going to color clusters 1 to 1. So just cluster 1 is going to be colored red. Disable that. All the rest of the clusters are going to be transparent. So if I zoom in here, only that cluster 1, that little 4 cluster, is colored red. Everything else is transparent. And the color of the rest of those transparent colors is determined by the uniform color. So if I wanted everything to be kind of pinkish, I could make that the rest of those pinkish. And I can set a second range that can be a different color. So let's say I wanted to look at cluster 3. I want that one to be green. Or I wanted to look at clusters 3 through 5, and I want those to be green. So if you had, for instance, a series of large lumps that you wanted to track, you could color just those lumps of specific color and make everything else transparent, and it's really great for tracking particles through the flow. And then finally, there is the work, the particle work, which essentially colors each particle according to the work performed on it. So the reason we're not seeing any work right now is because if I go to this work tab, my work type is not set to particle. If I just set that to particle, and again, I'm going to discuss this tab in a separate video. All right. So now if I color it according to work and just play back the file a little bit, now we're going to start to see some particle wear. Let's change my scale. Particle impact 0 to 1. It's kind of tough to see, but if I played back enough of the file, you'd see these particles start to have some wear values attached to them. All right. Next, we have our particle style, and the particle style is not the color of the particle, but it's the style of the actual spheres that we render. So if I zoom in here again, by default it's lumpy. I can hide the particles there if I want, same as hiding them from here. Changing it to hidden, we'll switch that to hidden. Lumpy is just kind of a lumpy looking sphere. You can see that those spheres look kind of lumpy. If I switch to smooth, it's a higher quality sphere. The lumpy one might look a little more realistic. It doesn't reflect the light quite as neatly as the smooth does, so it might be more realistic. Then there's specular, which is basically the same as the smooth, except we apply the specular lighting to it, so it looks really shiny. If I switch to meshed, this is pretty cool as well. What this does is it colors each particle, it meshes each cluster, so that rather than looking looking like a series of spheres, it's one giant mesh. And that's really cool because it looks better than just looking at a series of lumps. If I switch back to lumps, you wouldn't even be able to tell, well, where does one cluster end and the next cluster start. But if I switch to meshed, well, now we can see each individual cluster quite easily. Position tracers is really nice as well. What this does, if I skip a few frames, it draws a series of lines that show the center of gravity of each cluster as we proceed through the simulation. Right here I can set how many lines I want to show. So let's go back to, say, 5 seconds. Change my view. Okay, now let's go ahead and play. So I've got 3 lines right now, but what if I wanted to show more? Or what if I wanted to show less? What if I just want 1 line? Click 1. Now there's only 1 line. Back to 3. What if I want 10? I think the max is 9 actually. 9. Now those lines are going to get really, really long. But it allows you to track the position history of the cluster at the same time that you're looking at, say the velocity or the elevation. And obviously you can change this so that at the same time that we're looking at position tracers, I could be looking at I could be looking at the cluster types, or I could be looking at everything as uniform, or I could be looking again at the belt velocity or transparent. So all the particle coloring is independent of the particle style. So you pick your particle coloring and then you can choose whether you want them to be specular or meshed or whatever. And then lastly, a newer one that we just added along with our this lines one was added along with that adaptive degradation, because what that does is simply draws all the particles exactly as if we were in the adaptive degradation mode. So if we watch this, the playback is actually pretty quick for when we're just looking at lines, but if I switch that to, say smooth, well, now our rendering mode is, 25% of what it was before. So that lines is going to be the fastest rendering mode. Outline tolerance is the tolerance that we use for drawing these outer lines. So if I go ahead and hide all those particles, if I turn this down to 0, you can see there's a few extra lines that are being drawn in here. Now generally the outer lines that we're looking at, for the most part, most of those intermediate triangles that you can see in wireframe mode are hidden. You can't see those when you're looking at just the outer lines. But there are some that Newton tends to miss because of improper normal vectors or for some other reason. It just forgets to delete those lines. So just by applying, even just 1 degree of outline tolerance, we can just go ahead and skip all those intermediate lines. So what this does is it looks at 2 adjacent triangles and it says, well, the direction of the normal vectors for these 2 triangles, is it less, the difference between those vectors less than 1 degree or 2 degrees? If it is, then it deletes the line between those triangles. So if we look at this transition section, each of these triangles has a slightly different normal vector, but as I increase the outline tolerance, those lines are going to start to disappear. Same with the lines on the head pulley. As I increase this, those lines are going to disappear. So it just gives you a cleaner looking model. And the exclude layer simply says, well, is there one specific layer that I don't want to apply this outline tolerance to? Maybe I don't want to hide the outline tolerance on the feeder belt. So that's layer 8. So let's exclude layer 8 and then add a whole bunch of outline tolerance. You can see the lines on that feed belt are no longer disappearing because we're excluding that layer. Alright. Now over here on the end, this combo box is just like when we right click and we go to our orbit center of gravity. There's a few selections here, but this allows us to select the center of gravity of the orbiting can be any of the layers. So maybe I want it at the center of gravity of the feeder box. Boom. Now when I orbit my model, we're orbiting about the center of gravity of that box. Or maybe I want it to be the center of the head chute. What did we call that head chute? The head chute is rock box. Rock box. Now we're at the center of that head chute. So it's just an extended set of options for the same as this right-click menu here. Now, clip planes. Last thing to talk about. Clip planes allow you to show or hide specific particles or triangles, specific sections. So what you would do here is, let's go ahead and turn on my tolerance. Show my particles. Let's say I only want to look at the particles in this head chute. What I could do is I could set up a clip plane that will only show those particles. So I want us to click Show Clip Planes. That's going to show me the lines as I'm drawing this. And actually, for now, let's hide particles because it'll be faster. Now let's just say negative 5 to 5, negative 5 to 5, negative 5 to 5. Oh, there. And there's my clip plane box. Obviously, that's showing me more than I want to see, so now I can go ahead and adjust those. Maybe I only want negative 3, negative 2, let's say negative 2.5 to 0, 1, 2, okay. And in the Y direction, we want to go from negative 3, negative 2.5, close enough, to, say, 2, 2.5, okay. And in the X direction, we want to go from negative 1 to 1. Oops. Negative 1. There we go. So now there's my clip plane box. It's only going to show me the particles inside there, assuming I set it to do that. So if I go and turn those particles back on, we don't see anything because I haven't told it what to do with this clip plane yet. I've set the bounds. Now I got to tell it, do I want to hide the data, show the data in this box, or do I want to hide the data in this box? Well, I want to click Show Data in this box. So now what that does is that says we are always going to show everything inside this box, regardless of any of the other clip planes. All of the particles in this box will always be shown. I can say all the triangles will always be shown, or all the lines, or all objects. So right here I'm saying everything that's inside this box is always going to be shown. So now what I would do is I would set up a second clip plane. I'd say, well, I want to hide the data in this box. I want to hide all the objects in this box. And we'll just set the bounds negative 99 to 99, negative 99 to 99, and negative 99 to 99. Boom. So now what that did is we set up a huge clip plane that says I want to hide everything inside of it. But because we have a clip plane as well that is forcing it to show the data in this box, showing data always trumps hiding data. So we're always going to show the data in here. And you'll notice that we can see some extra lines because it's looking at the center of gravity of the particles and center of gravity of the triangles. So the exact bounds are not always precise. You might see a tiny bit of line or a tiny bit of triangle sticking out. But maybe, you know what, maybe we just wanted to hide the particles. Maybe we didn't want to hide the triangles. So let's just switch to this one that's hiding, say, particles. So now we're hiding all the particles in the entire simulation except the particles that are in this box. Or what if a common thing that we do when we're creating these simulations for our clients is we don't want to show the client this drop box because, well, the material is coming on a conveyor belt. It's not being dropped right here next to the chute. That's unrealistic. We don't want the client to see that. So what we would do is we'd say, well, okay, let's just go ahead and turn off these clip planes here. Let's make a third clip plane, and let's set the bounds for that. So our y bounds would be, say, -10 to -3, -2.5. Oops, no, -3.5. Okay. Our x value, we'll just say -3 to 3. Z value can be 0 to 5. Boom. Okay. Now I want to say hide the particles and lines and triangles. I want to hide everything in that box. And now you can't see where the material is coming from. Maybe I want to scoot this out to -4. -4.25. Sure. Go ahead and turn off those clip planes, and you've got no idea where the material is coming from. It just looks like a nice incoming flow. So that basically covers everything on this General tab. If you have any questions about the General tab that aren't addressed in these other tutorials, then feel free to send us an email at info@actek.com. Thanks.